Okay, so I wanted to make a recording about a particular old exam question that I think fits really nicely with the sort of the learning of the material, the in with the lecture, really. So let me share my screen. We'll just dive right into it. Here it is. This is from exam 2 of the most recent spring. That's listed in the list as 1920 spring. And specifically, we're going to look at question 6 down here. Here it is. And before we get into it, let me just show you where this comes from. This actually goes all the way back in a way to the beginning of chapter 4 in this theorem here. I'm sure you'll all remember that as long as certain regularity conditions are met, that the set of solutions to a homogeneous linear differential equation is an n-dimensional subspace of Cn. And now what I want to talk about here is the fact that it's n-dimensional. And you may recall that we never really proved that. We said that, well, this will be easier to prove later after we have more powerful tools. So let's wait and do it later. Of course, we did prove the other parts. So that proof is really what I want to talk about today in this recording. So this proof, of course, we all heard me talk about it in the lecture, but there's several parts. You have to set up some tools to work with. And then we observe that we have a linear transformation. We observe that it's 1-to-1 and onto, and then we cite this theorem from the previous page about dimensions. Okay, all right. So what we're going to see in this old exam question is that this old exam question is basically that proof. And so I'm going to go through the old exam question here and then point out, go back to the that portion of the lecture recording and point out how, yeah, it's the same thing. Okay, so here we go. So first of all, let's talk about the setup of this question. And let's see, I guess I'll zoom back in so we can see better. Look at the, just looking at the setup. So all of this right here. We have a vector space of solutions to the differential equation and then linear transformation from that vector space into R2, namely, what are the initial values corresponding to that solution? Well, in the proof, that is all of this right here, right? We have a vector space of solutions, and then we have a linear transformation into, given by this formula, into the vector space of initial values, which of course is Rn. Okay, so that all this stuff is just in the setup of the question. Okay, and it's sort of the setup to this proof as well. Okay, now let's, while we're here, I'll observe that the next thing that we did in the proof is to check that this is in fact, this thing here that we claim as a linear transformation actually is a linear transformation. So notice that is part A of the question, is show that that is a linear transformation. So we're really just doing the proof here. With certain guidance being given along the way, doing the setup, giving you the structure of the proof as part of the question, right? And I'm also giving some specifics. We're not proving in full generality. Here we're looking just at that right hand side, right? So keeping it more hands-on, perhaps. Okay, so that said, now let's go ahead and do this part of the proof. How do we know that this is a linear transformation? Well, this is what we would need to be true for that to be a linear transformation. That's the rules, right? And then it's just kind of a matter of writing down, well, what, for example, is T? Well, T says plug in 0 into the function in question and its derivative. Okie dokie. Well, here I'm just doing that, right? Plugging in 0 into the function in question. Oh, and I typo. Look at this typo. That's supposed to be I'll do this in red. That's supposed to be prime there. I'll get that fixed. So this is just plugging into t. Okay. Next, well, what is this? What is the derivative of a linear combination plugging in 0? Well, this is a single variable calculus problem, right? How do you take the derivative of a linear combination? Well, derivative of a linear combination is that same combination of the derivatives. It's Calc 1, early Calc 1. Okay, and likewise, this is just the definition of what it means to have a linear combination of functions. Okay, and then this next step is really just a bunch of Math 212, right? This is how you take a linear combination of vectors. Linear combination of vectors is done component-wise. And then we celebrate because, in fact, this is exactly by definition of t, that is t of f1. And this is by definition of t, exactly t of f2. So we get what we wanted. This is indeed that. And we have ourselves a linear transformation. Okay. All right. So going back to the proof that I claim that this problem models, right? We've checked that that's a linear transformation. For the special case of that, specific differential equation we're looking at, but it's just as true, and the argument is analogous here. Okay, the next part of the problem is, well, the next part of the proof, I'll say, is to check that this newfound linear transformation is both 1-to-1 and on-to. And notice the reason that it's 1-to-1, the reason that it's on-to is because in both cases of the existence and uniqueness theorem. Right. So given an initial value, what the existence and uniqueness theorem says, given any initial value, there's exactly one corresponding solution. Okay, well, that says given any output, the initial values are the outputs of this function. So given any output, there is exactly one solution, namely there's exactly one input. And that's what it means for a function to be 1-to-1 and on-to. Okay, so that's the argument that gets made now in part 2 down here. How do we know that T is bijective? Well, because of the existence and uniqueness theorem. Now, specifically, this question says, what theorem allows us to draw that conclusion? So here we indicate the existence and uniqueness theorem. And of course, we do want to check and make sure that the conditions apply. How do we know that this theorem applies? Well, we have to check its conditions. We need for the coefficient functions to be continuous. Well, they're constants, right? So of course that works. Let's see here. We need the right-hand side. Well, this is homogeneous. So the right-hand side is just 0. That's a constant. Of course, that's continuous. We need for that lead coefficient never to be 0. Well, it's 1, which is rigidly not 0, right? So all the conditions are satisfied. So we've checked those conditions. All right, so again, notice what we're doing here, right, is part B of the question is really just continuing on with the next part of the proof. Okay. The last part of the proof here was how does this fact allow us to conclude that the dimension is what we say it is? How do we know the dimension of S is in? Well, S is these two dimensions are equal because of this theorem, right? If you have a bijective linear transformation, then the dimensions of the domain and target are equal. We have ourselves here a linear transformation that is bijective, so the domain and target dimensions are equal. And then we just observe that, well, yeah, okay, don't forget that our target is Rn. And of course, it's perfectly clear the dimension of Rn is in. All right, so we're going to say something morally equivalent down here, part C. What does this allow us to conclude about the dimension of V? Well, it's a bijective linear transformation, and so the domain and target have the same dimensions, right? Just like we argued. The target is clearly two-dimensional. and therefore, as desired, our vector space of solutions must be two-dimensional. Okay. All right. So I really enjoy these kinds of questions. I think they make a lot of sense. They serve a really nice purpose. Questions like this allow me to check and make sure that students are, have understood the steps and the important steps in what, could be argued to be a hard proof without having to actually make students write out the hard proof. I mean, I think, if I were to say here, prove this theorem, maybe that's a little too hard of a question, right? So this allows me to guide students through that, and also to take out some of the generality, a little bit intimidating, right? We can see an actual differential equation here, right? It makes things like this part of the problem a little bit more hands-on as well. Okay. All right. So I hope that's been useful. Again, this is question 6 from 2020 spring. And let's see here. I guess we're done. Okay. Hope y'all have a nice day.